So we've talked in a casual way about small p-values and large p-values, but now we're going to start getting more formal about determining statistical significance. So let's just start by looking at this randomization distribution. And this randomization distribution is about a correlation. So in my null and alternative hypotheses, I have the parameter rho, which is like that p, but it starts at the bottom and loops around. And my alternative hypothesis that I'm interested in is the correlation truly greater than 0? And I have a randomization distribution. It looks relatively symmetric and bell-shaped. It's kind of going off the top of my plot here, but I think you get the idea. It's centered around 0 because that's the null value in my hypotheses. And if we look at this randomization distribution, I want to know which of these sample statistics would show the most evidence in support of the null, which would tell me that the null hypothesis was actually true, that the true correlation was actually less than or equal to 0. So would it be an observed correlation R of 0.1, an observed correlation of 0.3, or an observed correlation of 0.5? Maybe I'll zoom in a little bit so we can see the axes here. So if we're looking here, we've got 0, we've got 0.5, so this would be 0.25, 0.1 would be here. What were the other numbers we were looking for? 0.3 and 0.5. So if I'm looking for evidence that the null is true, that the true correlation is about 0, then the sample statistic that would provide the most evidence in favor of the null would be the one closest to the middle, the 0.1. So that would be the answer here, 0.1. And we'll talk about the other question in synchronous class. So the p-value, remember, is the proportion of the distribution that is as extreme or more extreme than the observed statistic. So if I have a distribution that looks like this, and I have an observed statistic here, then the p-value is the proportion of the distribution that is as extreme or more extreme. And this looks like maybe about 0.25, just visually. So if we have a small p-value, that means that a statistic as extreme or more extreme as the one we observed would be very rare if the null hypothesis were true. And that's going to give us a lot of evidence against the null. Versus if we have a large p-value, that means a statistic as extreme or more extreme is pretty common if the null is true. And that would give us not much evidence against the null hypothesis. So I would characterize 0.25, like I've kind of drawn on this picture, as giving us a pretty large p-value. It means that a statistic like whatever this number here is on the x-axis, that would be pretty common if the null were true, and I don't have much evidence against the null. So the smaller the p-value, the stronger the evidence against the null. So if I was going to draw myself several distributions, maybe I'll actually copy this one so they look exactly the same. All right, so if I had a p-value like this, that would not be very strong evidence. This would be a little bit stronger evidence. This would be a little bit stronger evidence. And if we were way out here in the tails, that would be the strongest evidence. So this is the strongest evidence, and this is the weakest evidence. And we've got a range in between. So when we're doing hypothesis testing, there's only two things that we can do in terms of our formal decision. So one is if we have a small p-value, we reject the null hypothesis, and that language is very important. And if the p-value is not small, then we're going to fail to reject the null hypothesis. And again, that language is very important. So we never say that we accept a hypothesis. If you were to put something like that on an exam, you would get the question wrong. So you need to say either we reject the null or we fail to reject the null. Those are appropriate things to say. It's not okay to say that we accept the null or we accept the alternative. We're going to use our significance level, which we're going to denote alpha. So alpha is the Greek letter that looks like this. I start at the top and I loop around. It's sort of like a Greek A. So alpha, that's the threshold that we set for our p-value. So if our p-value is less than alpha, we're going to reject the null. And if it's above alpha, we're going to fail to reject. So I've kind of summarized this here. If it's less than alpha, we reject, or if it's greater than or equal to alpha, we fail to reject. And often, alpha is equal to 0.05 unless it's otherwise specified. So if I, on an exam, don't tell you what alpha level to use, you can just assume 0.05. And the question is, why 0.05? So one answer is that 0.05, alpha equals 0.05, it corresponds to 95% for a confidence interval. So basically the alpha equal 0.05, that's for hypothesis testing. And the 95% confidence level for the confidence interval, those are kind of two sides to the same coin. But there's a really nice explanation on this Open Intro website, and I'd like you to go through it. So pause the video here, go to the link, which I've also given you on Canvas, and go through the activity. So when you go to that website, you're going to start with this short video that you're going to watch, and then there's going to be an activity and another little video. So again, pause the video, go do that, and then come back. Okay, so hopefully now you have an idea about why we use 0.05. And we have our two formal conclusions to the test: reject the null hypothesis or fail to reject the null hypothesis. Those are known as generic conclusions. So if I ask you what's the generic conclusion, you're going to give me one of these two options. But oftentimes we also want a conclusion in context. And a conclusion in context is like a sentence about the real world implications. So like we have evidence that, and then you'll fill something in from the alternative hypothesis, or we do not have enough evidence to conclude that something is true. So if we have evidence, that would go along with reject the null hypothesis, and we do not have enough evidence, that would be fail to reject. So those are the sentence starters for the conclusion in context. So I'm going to go back to my example about the atheist shoes. Remember, they ran that experiment. They sent out packages, 2 packages each to 89 people, and they looked to see how long it took them to arrive. So let's go to StatKey and just remind ourselves what the randomization distribution looked like for that example. So I'm going to go to randomization hypothesis tests, test for difference in means. And since this data set doesn't come in StatKey, I'm going to need to upload the data. All right, let's generate 1,000 samples. So this was our randomization distribution for the atheist shoes example. And we've looked just visually at this distribution and determined that the observed statistic of, I think it was 3.04, that would look very extreme on this distribution. If I wanted to, I could actually ask StatKey to tell me how extreme that number was. So 3.04, that would be off on the right tail. So I'm going to click the right tail button. And then I'm going to change from this 1.207, I'm going to make that the 3.04. Okay. And so then it kind of shifts the axes a little bit, and it shows me that the p-value is approximately 0. So we had kind of concluded that already. If we had found a difference of like a day and a half instead, I could have put in 1.5. Okay. And my p-value would have been 0.008. So the p-value that you get depends on the observed statistic that you saw. I'm going to put this back to 3.04, and I will put a screenshot into my notes. All right, so here we are. Our p-value was approximately 0. Our null and alternative hypotheses had been that mu for the branded tape minus mu for the plain tape was equal to 0, or mu b minus mu p is not equal to 0. My generic conclusion is going to be to reject the null hypothesis. And my conclusion in context, we have evidence to suggest there is a difference in arrival times based on the type of tape used. And it turns out that there are actually some pretty big studies about anti-atheist bias in the United States, so it's possible that that's what's going on, that people are either consciously or subconsciously not processing those packages with the branded tape as quickly. I think that the company actually stopped using that tape as a result. So we've got our p-value, our generic conclusion, and our conclusion in context. So we've done our hypothesis testing. Looks like I gave myself some space to write, but I already did it on the last slide. So there's a term that is statistical significance, and if our p-value is less than alpha, we're going to reject the null, and we're going to say that the results are statistically significant. So in the atheist shoes example, our p-value was approximately 0. 0 is less than 0.05, so the results are statistically significant. So the basic idea of hypothesis testing is that you start by stating the hypotheses. So that's going to be writing out the H0 and the HA, whatever they are, in words or probably in symbols. Then you're going to compute and record your observed sample statistic. So that might be an X bar, it might be a P hat, it might be an X1 bar minus X2 bar, it might be a P1 hat minus P2 hat, etc. Lots of different possibilities. Then you're going to find the p-value, and this step is hard and important. So finding the p-value actually means a lot more than just one step. If you're going to use randomization, that means you need to go mix up the values of one of the variables, compute and record the randomization statistic, repeat that process 1,000 times, look at your sample statistic in the context of the distribution, and then see what proportion is as extreme or more extreme. So this piece, there's actually a lot hidden in there. But once you've found the p-value, then you're going to make a generic decision, and you're going to interpret the conclusion in context. So that's kind of the big picture with hypothesis tests.